Hey everybody. Today we're talking about conditional probability and the multiplication rule. We're in a situation where we know that one event, A, has occurred, and we're interested in the probability that another event, B, occurs, given that information about A. For instance, suppose we draw two cards from a standard deck without replacement. Let A be the event the first card is a king, and B the event that the second card is a king. The conditional probability of B occurring, given that A has occurred, is 3 in 51, because after the first card has been drawn and turns out to be a king, there are 3 kings left out of a total of 51 cards. So that probability ends up being about 0.059. A bit more formally, the probability of B given A is defined to be the probability of A intersect B, so A and B, divided by the probability of A. Obviously, that's only meaningful when the denominator there on the right side is non-zero, but that's logical since we're supposed to be computing the probability of B under the assumption that A has already occurred, so it makes sense that would only be defined if A is a possible event. By the way, in the situation where we have a finite sample space and all the outcomes are equally likely, that right-hand side can be interpreted as the number of outcomes that are in both A and B divided by the number of outcomes just in A. And that corresponds to the Venn diagram we're seeing here. We're in a situation where A is sort of our universe. Only the outcomes in A are possible. And we're interested in the probability that B occurs under that assumption. So the probability of B given A is the fraction of the shaded area in this Venn diagram that's darkly shaded. A different sort of example. A researcher contacts 1,250 adults at random and asks whether they prefer dogs to cats. They also have it broken down by age into 3 different categories. And the results are shown in this table. Find the probability that a respondent over the age of 55 prefers dogs. So as usual with my example problems, I recommend pausing the video, trying it on your own before seeing my solution. Let's let B be the event that the person selected prefers dogs, and A be the event that the person selected is over 55. So with that notation, we need to find the probability of B given A. And of course, that's the probability of A intersect B divided by the probability of A. In order to get that, we're going to count the number of respondents that are in A and B, so over 55 and prefer dogs, that's 143. And then we'll get the number of respondents that are the number of outcomes in A, the number of respondents that are just over 55, and that's 325. So the probability of A intersect B divided by the probability of A is 143 divided by 325, and that's 44%. Conditional probability is particularly useful when calculating the probability that 2 events both occur. The multiplication rule says that the probability that 2 events, A and B, both occur is given by the probability of A intersect B equals probability of A times the probability of B given A. Basically, find the probability that the first event occurs, then assume that it happened, multiply by the probability that the second one occurred. For instance, going back to that deck of cards, let's draw 2 cards again, but now let's find the probability that both draws are kings. Using the multiplication rule, we will find the probability that the first draw is a king, 4 in 52, and then multiply by the probability that the second draw is a king under the assumption that the first is a king, and that's 3 in 51. Multiplying those 2 fractions together, we get about 0.0045. Here's a different sort of example. A server at a restaurant has observed that the chance that a customer orders alcohol, call that event A, is 40%, and the chance that they order an appetizer, call that event B, is 30%. The chance that they order both is 20%, and we'd like to find the probability of B given A and the probability of A given B. We're going to start with the multiplication rule here. The probability of A and B is the probability of A times the probability of B given A. And we know some of those probabilities we can just plug in. For instance, the probability that they order both is 20%. Once we've plugged in, we can just solve for the conditional probability. The probability of B given A, the probability that they order an appetizer given that they ordered alcohol, is 1/2. We can do this the other way around as well, just flipping the roles of A and B. The probability of A and B is the probability of B times the probability of A given B. So again, plugging in, simplifying, we get that the probability of A given B, the probability that they order alcohol given that they ordered an appetizer, is 2/3. Notice that the 2 conditional probabilities are not the same, and that's almost always the case. That makes sense because in the one case, we're talking about the probability that they ordered an appetizer under certain circumstances. In the other case, we're talking about the probability that they ordered alcohol under certain circumstances. So, pretty different phenomena. One last example for you to try. A card is drawn at random from one standard deck and then placed into a second deck. That second deck is shuffled, and then a card is drawn at random. What's the probability that that second card drawn is a king? So on each of the two draws from the first deck and then from the second deck, we can either have a king, we'll call that event K, or a non-king, call that event N. So we need to find the probability of getting a king and then a king, or a non-king and then a king. In order to do that, we're going to use the addition rule. These are disjoint events, king, and then not king and king. And we'll compute the probability of each of those two things, king and king, not king and king. In the first case, it's 4 in 52 times 5 in 53, because after the first card is a king, there are then 5 kings in the second deck out of 53 cards total. The probability of getting a non-king and then a king is 48 in 52, because you haven't gotten a king from the first deck, times 4 in 53, because now there's 4 kings in that second deck out of 53 cards total. Doing a little simplification here, we get 1 in 13, which happens to be exactly the probability of drawing a king from a single standard deck. So the probability is exactly the same as if we hadn't gone through this whole exercise of drawing a card from the first deck, putting it into the second.